This is our first office hours session for the August 2017 5-axis post class. So this is office hours, day 1, session 1. So we had a question from Zeke asking about the rot axis direction settings. Down in the top of the post, in the variables that we use to set up the post, are probably the two most important sets of variables in regards to how does Mastercam calculate the rotary axis angles. When we look at the way that they've set up the logic, we define the axis of rotation in terms of two vectors that are perpendicular to the actual axis that is rotating. So Zeke says, if I understand correctly, rot axis $1 must be set to one of the axes that is not the actual primary. That is absolutely correct. So here we've got one line that is facing the x direction, positive, and one line that is facing negative vec y. So if we look in Mastercam and we draw that, go into the top plane and make sure that we're in the top plane. We are. So I'll go to wireframe and I'm going to draw two 1-inch long lines. And let's make this one red, and we'll leave that one green. So what we're saying is we are describing a plane that is perpendicular to the axis of rotation. And we're saying with this code here, we've got positive vec x, we've got negative vec y. So negative vec y, this actually gets reversed. So with our current setup, we've got a z-axis, and the z-axis starts with its 0 here and rotates towards negative vec y. Yes, it's the plane that is being rotated that is described by these two vectors. And the important part about the 0 point is how do we take a tool vector. In other words, NCI G code 11 describes the position of a tool in space relative to an origin point. So let's do this. So I'm going to create a point. And we'll make it 14.25 in X. 6.325 in Y. And 11.2 in Z. So we go into 3D mode. Ooh. Let's go. Yeah, there we go. I'm going to rotate this thing around. So what we have here, actually, let's move it a little closer to the origin so it's easier to see. Okay. Just wanted to get a little bit closer to the origin. All right. I'm going to load up a copy of the machine, and we're going to drive a tool to cut this line with two different angles for the tool vector, and do toolpath multi-axis curve. We use the same 1/2-inch ball end mill. Cut pattern is a 3D curve. That's what we're going to cut. And tool axis control. Oh, we'll do this too. We'll do compensation computer. We're going to do compensation direction left. And then radial offset is half the distance of our tool. We can actually set a different radial offset. Curve 5-axis will let you move the tool through space however you want. It's like a contour toolpath, but with the ability to control the axis or the inclination, if you will, of the tool. Under tool axis control, we get a bunch of different methods. How do you want to control the tool? Do you want to use lines to specify where the rotation changes place? You can use a surface, you can use lines, you can have it be normal to a plane, which essentially gives you three-axis like motion with the tool locked to a particular angle. You can also do from point, to point, and chain for your tool axis control methods. All of these options in the toolpath dialog simply tell Mastercam how do we want to position the tip of the tool relative to the geometry, and how do we want to rotate the axis of the tool, in other words, the center line of the tool, relative to each point along the toolpath. So we'll use lines. We'll make sure those two lines are pointing away from the tip of the tool. In other words, back up towards the spindle. And I've still got my tool created with the gauge length of the tool so that we know the pivot length of the machine itself. All this stuff should be fine here. Let's get rid of the oscillate. So if we look, the tool starts out aligned to the z-axis of our WCS. When I hit the S key, back up a second. When I hit S to go to the first step, the tip of our tool is located 4 inches above this first point where we told it to cut, but it is 4 inches along the tool axis. If we look in the top view, we are rotated in respect to Z. So we're describing that perpendicular plane with those vector directions. And what the post processor does is takes these vectors that we are actually outputting. So if I hide the tool and I turn on the vectors, and let's make them like 3 inches long so we can see them, and we'll do the shading. So here's the tool. Here's the tool vector, which is the center of our tool. And as we approach this part, we're aligned with that orientation. Again, if we look from the top, we've got an angle here. And if we look from the front, we've got an angle this way along the B axis as well. So how do we go about calculating the relative position of not only the tip of our tool, but in our case, we're actually calculating the pivot point of the machine. So what we don't see represented here is our actual real setup, right? We've got this tool that represents what is essentially the A-axis spindle motor, right? Because this is going to be the pivot point of the machine. So our head is going to be located in this area right here. The A-axis, or actually in our case, this is a B-axis spindle. So we're using a CB. B-axis is going to be pointing down here. And our tool, with our tool holder, is actually going to be somewhere around here. So that's kind of, you know, the only disadvantage of doing this style of describing the tool length, is that if we use the overall length of the tool, we don't get a realistic representation of the tool. Sometimes when I set up a gantry machine like this, I will actually draw a custom tool definition. And as the tool itself, I will draw the entire profile of not only the tool, but the holder and the rotating components of my spindle nose. And even behind that, you know, along the tool axis, draw part of the body, just so that you get an idea that you've got this big mass swinging out there. It's a little bit easier to see if we go and use the machine simulation from Mastercam, because then we can just load that info into Mastercam, program it with a tool like this, and then when we put it into the machine simulation, you get a much more realistic idea of what is happening kinematically on the machine. How is the machine moving around? Because here, our tooltip, you can see I've got a little bit of angle between these two lines here. Down here, it looks like a relatively small motion. The problem is when we visualize it with the actual long tool, you can see here's the back end of the tool at this point, and then by the time we swing over to this other vector, you know, we've moved like 3 or 4 inches up here. We've only moved maybe a 1/4 inch down here. So how does Mastercam take these relative tool positions and calculate the angles from them? We have to think in terms of our planes that we're setting up, right? The 2 vectors that are perpendicular to our axis of rotation. One of the things that we deal with internally inside the post is a bunch of mathematical functions that use vectors as their input. And specifically, they're unitized vectors. In other words, they have a vector length, a 3D length of 1 unit. And when that's true, when they have a 3D length of 1, it gives it some special mathematical properties, because we can take the delta values in X, Y, and Z, square them, add them together, and take the square root of the number in order to derive some properties. And part of what we get is access to the atan2 function, which helps us calculate the angle. If we think about this in terms, in functional terms of the, of the unit circle functions, let's look at this first vector here, and we're not going to do the code yet. We're just gonna do a thought experiment in terms of what kind of process do we go through to actually calculate this angle. So what I'll do is I'll take this line here, and I'll translate it back to the unit circle. In fact, I'll get to that one in a minute. We'll do the unit circle thing. So I'm going to make a copy of that vector in space, and I'm going to move it back to the origin. So we've got this tool position, and we want to derive the angles to be able to tell the machine, hey, if you move your B axis to this angle and you move your C axis to this angle, we're going to position the tool the way that we want it positioned. So what happens? If we use a Z axis straight up and down as our primary, what we need to be able to do mathematically is rotate this vector into the plane of rotation. So our rotary for the secondary is a B. In other words, it rotates about the y-axis. We therefore need to rotate this line into a plane that's perpendicular to y. So it has to be aligned to z and x. And watch what happens. The primary, again, is just the mathematical function that gets calculated first. So first we're going to take this angle starting at 0, this line, and we're going to rotate it mathematically back so that it's aligned to this plane here. And this is exactly the way the math functions in the post. So we're going to do a copy of it. And it's somewhere in there. Now I could do the math to figure it out, but I'm just trying to show you conceptually what happens. Zoom in nice, we get a nice clean view. Okay, so we're using those two vectors in X and Y to describe that z-axis of rotation. So we take our tool vector and we make our first rotation, the primary, back to the X and Z plane. And we do that because we're next going to rotate it about Y, which is B. So here we're all in top. If I go back to the planes, we're in top, everything's good. And I say copy it, okay. Boom. So now we've got that tool vector that has been rotated in the primary to meet up with Z and X. So it's been rotated into this plane, and this plane is the B, right? It rotates about Y. We can tell it rotates about Y because there is no Y in either of these two entries right here. And that's like really the secret of understanding the two vectors. The two vectors are always perpendicular to the actual axis of rotation, and the way that we rotate on the plane, it always rotates from whatever vector we say is the 0 vector to whatever vector we say is the direction. So we're rotating from negative vec z to positive vec x. If we look at those vectors, go back to the levels here. Okay, so again, this was our top when we said, okay, our rotation is from, where do we go? Positive vec x to negative vec y. So you can see that our rotation happens in this direction. So in terms of our z-axis, we've said if I start here and I rotate that way, that is positive. So we're always describing which direction is positive. In this case, I said we're starting at plus x and we're rotating towards minus y. Now, if we were to go in here and we wanted to go the opposite direction, we would change the sign. And when that happens, that's what happens. When we reverse the sign, when we change the sign, we reverse the rotary direction. So this again was rotating about z. We rotated from positive x, that's vec x, to minus vec y. And that was our first, that's how we first rotated our vector. And this is b axis rot axis, rotor. So we did, this one's the z-axis. Z. Okay, so we looked at that one. And if we look at our definition for our b-axis, we go into isometric, and we're going to go to the front plane. So in the front plane, we have minus vec z rotating towards positive vec x. So if I go wireframe, let's make sure we're at z0. Usually you can turn this off, which is okay. Well, as annoying as that is, just do this. Okay, if we look at this from the front, what we're doing when we go to look at our tool vectors, here's the vector that I rotated. So let's make that one orange, I guess. So we started in the top and we rotated this vector until it aligned with our plane. And so now if I look at this in the front, we're going to do this. We're going to move this guy to 21. And this is, 21 Okay, this is the tool vector on the z-axis plane after the first rotation. So this vector here has now been rotated into our plane. And if we look at our plane definition, the way that we described it in the post, minus vec z rotates positive towards vec x. That means that we rotate this way. Right? So we want to end up taking this vector now in the plane that's perpendicular to the b-axis, right? Which means we're rotating about y. We're rotating about y because there is no y in this rot axis 2 or rot dir 2. Just like here with rot axis 1 and rot dir 1, we're rotating about z because there is no z here. So here we need to rotate this line in order to bring it aligned with the spindle how it is when it's at 0, essentially, because what we're doing here is just calculating the angle. So we're using this vector to calculate the rotary angles that it will take to position the tool where we want it in space. It's a weird concept, but that's what we end up doing. So transform dynamic, this guy, and copy. And so here's what ends up happening. We end up rotating at approximately, 41 point something degrees. So before it was like a 28 degree move, and now it's like a 41 degree move in order to be able to get that vector translated back into position. So what we just looked at there was oh wow. If I go top, no. There we go. That's better. So green is our first rotation, right? We took this green guy and we rotated it based on our two vector directions until it was aligned with our plane. Then we use this definition down here, minus vec z rotating towards positive vec x, to rotate this orange guy until it was back vertical. And that's what we end up doing with these two sets of values, is we just describe two planes of rotation using two perpendicular vectors. And what's important for us is to make sure also that this 0 point is in the right position. And you'll tell if it's in the right position using simple geometry. So when we looked, originally at setting up this post, I use, a cylinder and a circle to be able to drive a 360 degree rotation where I'm locking the other angle at either positive or negative 90. And what's important is to check the actual rotations on your machine and then make sure that those two things match, right? That the actual rotation that you're getting on the machine is what is matching your code. And that's what this whole thing is about. And really, you can only do it through going out and testing at the machine. So go out to the machine and drive it in the manual jog mode, drive it in handle mode, and drive it in MDI. Make it position and go to different rotations, and that will help you discover, along with the manual, what the limits of the machine are. Because once you get the vectors set correctly, the rest of the stuff falls into place really easy. And by rest of the stuff, usually it is setting the rotary axis limits, setting things like primary angle output and secondary angle output options, whether you allow positive numbers or not, those kinds of formatting questions. But really, this is the heart and soul of the post right here. Using the M-type variable, setting up road axis direction and road axis, rotor and road axis, basically. Okay, cool. Well, that was a good question. I know it was really quite a long-winded answer, but hopefully it helped shed a little light, Zeke, on the way that these two vectors are used to set up the machine. Now, the other thing that you'll find, I think it's important to note as well, there's some additional information on how to do this in that PDF file, the 5-axis PDF. So with the 5-axis PDF, it talks about doing what we just did, but this to me is really not very intuitive. When you actually work through it and you create the vectors in Mastercam and think about the rotation of, all right, I've got a tool position in space, I'm going to rotate it mathematically around one axis, then I'm going to rotate it mathematically around another axis. And how does that work out? It helps bring it together, I think. One of the things that we've got in here is some really nice pictures that show different types of machine setups. So type 0, this is a table vertical, right? It's a pretty standard Haas with the VFTR series Trunnion. Same exact mathematical configuration as a machine like this, where we've got an A-axis platter here that then rotates on this B-axis table. The one thing that's different here is that the spindle in this case is aligned to the front, and we actually have, where'd that guy go? There it is. The only thing that we haven't talked about yet is horizontal versus vertical. How do we do that? I'll make sure that I go over this again in our regular class time, but there is a matrix called the machine base matrix. MATB, where is it? Yeah, it's MATB1 through MATB10. So the machine base option allows the NCI input to be mapped into a different coordinate system in the NC output. Alter the matrix settings to a view that is the target output. This is helpful for machines with left-hand coordinate systems or horizontal machines where the user prefers a setup relative to the machine tool. In other words, you want to be able to program using the top front combination because visually you get to see the spindle coming in horizontally like it is in the real world. So they give you this option on how to do it. What we get is a series of 9 variables in a row where each triplet of numbers represents the endpoint position of a single vector. 1, 0, 0 means we have a line that is 1 inch long in X, 0 in Y, and 0 in Z. So it's a 1 inch long vector that points to X positive. 0, 1, 0 is another vector line that is aligned to the positive y-axis, and 0, 0, 1 describes a vertical. This series of numbers in a matrix form, 1, 0, 0, 0, 1, 0, 0, 0, 1, describes a top WCS, where Z points up, X points right, positive. Z positive points up, X positive points right, Y positive points away from you. For a horizontal, we look at the next page. This example shows a horizontal machine setup, where the user prefers a setup relative to the front view in Mastercam. The user can now program the toolpaths with the part relative to the machine 0 as shown below. The post configuration settings are relative to this matrix. So what this allows you to do is to program with a top WCS and to use the front tool and construction plane as the 0 position for your spindle. So now creating tool planes is a rotation of the front plane instead of a rotation of the top plane. And you can see that this configuration is 1, 0, 0, 0, 0, 1. So 1, 0, 0, 0, 0, 1, and 0, negative 1, 0. Kind of coming up at the midpoint of our typical office hours. I would like to put it out there that normally we're also looking during the office hours times for questions and feedback from the students. So really, this is me trying to put some time aside to answer your questions. If we find during class as we go through it that there's not a lot of stuff, maybe because I don't know, I'm covering it so well, that we'll shorten the office hours a little bit, because again, this is really time for question and answer as opposed to regularly scheduled lecture time for the class. All right, let's go ahead and take like a 10-minute break. If you guys have questions about anything I've covered today or anything else that we've covered through class, or any other questions that are relative to programming a 5-axis machine, like hey, how do I do this, or even a 4-axis when it comes to rotation and positioning and setting up Mastercam to get the code that you want out of the post, that's what this class is about. So question. You know what? Let's deal with that when we get back from break. So thanks for asking a question. That's great. And we will, cover all the questions we get. So if anybody else has questions, please type them into the chat box. And I'll be with you guys here in, about 10 minutes. Between 10 and 15. Let's take a decent break and then we'll get right back to it. All right? Thanks, guys. I'm going to stop the recording and we'll continue on in a little bit.